Let us move on to MIMO processes. So far, we have seen SISO process, single input, single output process. If you consider if a level process means its output is level, input is valve opening or VFD or the speed of pump. Depends upon the design. In our lab, we have a level process. We are manipulating the inflow rate by using the valve. In that case, input is valve opening and that inflow rate through that valve opening, and output is level. That is called SISO process, single input, single output process. But many of the process in chemical industries are MIMO process. For example, if you consider distillation column, it has the top product is one process variable, bottom product another process variable, feed flow rate another process variable. Then these are all the pressure inside that temperature, pressure inside, or the process variable, pressure and temperature. Because to maintain the quality, we have to maintain temperature, pressure inside the distillation column, and the top product vapor flow rate and the liquid flow rate and the bottom flow rate, all the four are manipulated variables. In that situation, how many variables we can control is very important question. In a distillation column, how many variables we have to control to maintain that entire distillation column under 100% in our control? How many variables? Because a lot of variables are there in that distillation column. How many variables we have to control? It should not be over controlled. For example, only 5 variables alone can be controlled. Means if we control 6, then it is called at least any 2 will contradict each other. For example, I have 2 controls. One is today I am announcing, tomorrow you have to write test. In the 11th hour I am announcing, evening 6 o'clock I am announcing that you have to write a test tomorrow. But you should not burn your midnight oil. You should not wake up and you should go to bed by 9 o'clock. You have to write the test well. It's a contradicting nature. Because we want to control both. You have to perform well in the test, that is expected one by everyone. At the same time, you should not. You should go to bed early. It's contradicting nature. That's why we cannot control both. It's not possible. In the same way, if you do that, if you instead of suppose a process we can control only 4 variables. In that process, suppose you try to control, you designed 5 loops to control 5 variables. Means any 2 are there will be a contradiction among those variables may occur. That's why it is very, very important to find how many process variables that can be controlled in a MIMO process. First of all, we must know what is MIMO process. Many inputs, many output process. For example, in the distillation column that we have seen yesterday, how many are in the flash drum that you can see here? Here, how many inputs are there? The feed flow rate, temperature flow rate, the feed pressure, like that. Many inputs here. The steam temperature, steam flow rate. These are all inputs. Here, the vapor flow rate. Similarly, here, the liquid flow rate from the bottom product. These are all outputs. So, in a flash drum unit that we have here, many inputs and many outputs. This is an example for MIMO process. even though some of the process that we consider as MIMO process, we can see a single loop as a SASO process. That is also possible. All other variables in that process may be taken as disturbance for this particular loop. That way also we can see the MIMO process. Sorry, SASO process. One loop only we have to consider. All other variables will act as disturbance to that loop considered, single loop considered. How many variables that we can control is equal to degrees of freedom. The degrees of freedom for a given process as independent variable that must be specified in order to define the process completely. It means there should not be any independent variables. If if you define all variables, suppose a process has n number of variables. If you control, if you define by equation n minus 4 variables you defined, the remaining 4 variables undefined. In that case, the 4 variable, the process isn't under control, 100% control. It is not completely specified. It is not completely specified. In other words, it is not 100% control because 4 variables are independent variables. Suppose you put 4 loops to control that 4 variable means, then it is completely specified under complete control. That's why degrees of freedom means how many independent variables that we can find. That is the degrees of freedom f equal to number of independent variables minus number of equation that relates those independent variables. That is called degrees of freedom. Suppose I am having in matrices, you might have studied. Suppose 3 unknowns are there. How many equations required to completely define that? 3 equations. That is, then only the 3 equations will be consistent. Sometimes 3 equations will be consistent. If you have 4 equations means this can be reduced. One of them may be mirror image of one of the equations. The fourth equation maybe one of the mirror image of one of the 3 equations. Mathematically, we can find that. Suppose it's not the mirror image of any one of these 3 equations, then the fourth equation will be odd man out. In that case, inconsistent equation that we'll say in matrices. Like that, here the number of variables equal to number of equations means degrees of freedom is 0. That's why the system is completely specified, completely under control. That's why how many control loops we can put in a process can be defined the number of variables minus number of equations. So V minus E. That is F equal to V minus E. V is number of variables and E is number of equations, number of independent equations physically relating the V variables. Independent equation means, suppose you are writing one equation and suppose the second equation must be independent of the first equation. It should not be it should not have any relation with that. It should not be the manipulation of first equation. That is called, it should be independent equation. E independent equations are there for E, V independent variables, then degrees of freedom equal to V minus E. Now let us determine the degrees of freedom for a flash drum. Here our aim is not going to obtain the mathematical model of this flash drum. What are the equations that we will take it as granted, and you will find the degrees of freedom. If you write an equation for mass balance, you will get this the amount of mass accumulated inside equal to inflow rate total inflow rate minus total outflow rate. That is vapor outflow rate minus plus liquid outflow rate. And if you subtract these two from feed flow rate, you will get rate of change of mass inside that flash drum. So you got one equation. Here, if you write the expression for component balance, you will get n minus 1 equations, n minus 1 equations. Similarly, if you write heat balance, you will get one equation. Here, this is the amount of heat accumulated inside the flash drum. This is the amount of heat supplied by feed. Feed also supply heat. You know, it carries some heat and entering here. It carries some heat, heat and entering here. That's why heat supplied by the feed. Heat taken away by this amount of heat taken away by this vapor, amount of heat taken away by this liquid, and amount of heat supplied by this steam. Amount of heat supplied by this steam. That's why plus amount of heat supplied by this steam. These two are minus because it take away as a vapor product. It take away some heat as a bottom product, top product, and this is heat taken inside by this feed. So if you combine all this, you will get heat balance equation. That is another equation. So many, how many? This is n minus 1 plus 1 n plus 1 equations you are getting. If you write vapor liquid equilibrium relationship, you will get another n equations. You will get another n equations. Here n minus 1 n equation. So n plus 2n plus 1 equations. Here you will get two more equations for consistency constraint. If you write that, two more equations. So 2, 1 plus 3, and this is n. So 2n plus 1 equations we are having. 2n plus 1 equations we are having. How many variables that we are having? All the relationship above constitute a system of 2n plus 3 equations. Sorry, how many? Sorry, I said 2n plus 3. 1, 2, 3. 3, yes. 1, this is 2, and this is 3. This is n. This is n minus 1. If you add these two together, you will get n. n plus n, 2n plus 3. So total number of equations for this flash dummy is 2n plus 3. So number of independent equations are 2n plus 3, and with the number of variables equal to 4n plus 14 variables. Number of variables in that process is 4n plus 4. So in xi, how many xi's? N xi's, n yi's, n minus 1 zi's, and n ki's. If you consider all these together, 4n minus 1 variable and another 15 variables, area of cross section of the flash drum, area of cross section of heat exchanger, that's through that surface heat is transferred, rho density and heat transfer coefficient. Like that, how many? 14 such variables are 2n plus 14 variables are there. Among them, n plus 7 are constants. N plus 7 are constants. Initially, we thought that they are variables, but if you, what is how you will write a constant? A is a constant. It means what? A equal to, what is area of cross section? 5 meter square. Like that, if you write, what is the meaning? This is one equation. So like that, for constants, you will get n plus 7 equations. So this can be subtracted from this for the variables. N plus 7, if you subtract, you will get only 3n plus 7, 3n plus 7 variables. Then externally specified, that is also there. Externally specified means you can consider, for example, random variables. Those are all externally specified. We cannot specify. For example, the temperature of feed. How we can define? This is depends upon the ambient temperature. So the temperature of the feed is TF is a random variable. So like that, n externally specified variables are there. Similarly, zi's, n minus 1 zi's are externally specified. So n variables are externally specified. If you subtract them, you will get the remaining. Then unspecified, if you consider, unspecified are 2n plus 7. 2n plus 7. So if you subtract this n and this n, you will get 2n. and another 7 variables you can subtract from that. You will get 2n plus 7 unspecified variables. In other words, actually the variables are unspecified variables are 2n plus 7. How many equations we have? We have 2n plus 3 equations. We have external specified also we can tell like this. Tf equal to ambient temperature. Ambient temperature, like that we can write. No, that is also equation. So they are but ambient temperature, temperature we do not know, unknown disturbance. So this is also equation. Like that we can have only 2n plus 7 unspecified variables. That is 2n plus 7 unspecified. Number of equations are 2n plus 3. If you subtract 2n plus 3 from 2n plus 7, you will get 4. So therefore, in this flash drum, you can implement a maximum of 4 loops. You can implement a maximum of 4 loops. If you put the 5th loop, sometimes it may contradict to some other controller. Already I told you an example. Suppose one variable try to increase the temperature, another loop at the same time want to decrease the temperature, means it's contradicting each other. That way it may happen. That's why the maximum number of variables is equal to degrees of freedom. In other words, degrees of freedom is the number of variables to be specified to completely define that process is degrees of freedom. So then if you implement 4 loops, then 4 variables are defined. For example, I am having y equal to how I am defined through the controller, error multiplied by m of t. M of t is some other variable. M of t is another variable. So this way, if it is a proportional controller, I can define one y1. Another y2 can be defined by error multiplied by instead of putting m controller 1, another controller m2. Like that we can define 4 such variables so that the process is completely specified. The process is completely specified. Then there are how many variables are there? Unspecified variables are 2n plus 7. Out of how many that we can control? Only 4. How to select 4 variables from 2n plus 7 variables? That is a challenging task. How to select the 4 variables from 2n plus 7? That is a challenging task. That is the question. But which 4 of the 2n plus 1 unspecified will be selected as controlled output? How to select that? That we have to analyze qualitatively. We have to analyze that qualitatively about distillation column. What and all has to be controlled to get quality product, or what and all has to be controlled for safety aspect. What and all have to be controlled safety aspect. What and all have to be controlled for quality of product. What and all have to be controlled for maximize the controller production, maximize the production, optimization. So in that way, it depends upon the operating requirement. Are you going for quality of product? Are you going for optimize the production, or are you going for safety operation? Depends upon, we have to select the variables out of 2n plus 7. The operating requirements dictate in this case, in this distillation column, we have to maintain the P and T, because you know that P and T are very important. The boiling point of this top product, for that temperature T has to be maintained at P, at pressure P, at the pressure P. Because if pressure increases, you know that boiling point also increases. That's why at this pressure P, this is the temperature required to evaporate this top product. So this P and T are important variable, must be controlled. So out of 4, we know that 2, the other 2 how to select. That we'll discuss. The two variables we must um, are T and P. It is to achieve the desired separation, because at P at pressure P, the temperature must be 2 to separate the product, the top and bottom product. Then now we can have other things. If you want to have a constant production flow rate, the outflow rate must be constant. Outflow rate required means you should maintain the flow rate of the liquid feeding into the system. So here, if here this feed, the feed flow rate must be maintained so that you will get constant output, constant output to get that. Or in other words, to control the output, this feed is very important. This should be maintained constant to get a constant production. So now from this we can understand that it's the feed flow rate must be controlled, and finally the liquid should remain within that certain bounds. For example, it should not flood. This level should not go above certain value for safety as well as for avoid flooding. So this level should not go above. So we have to consider this level also. Level also. It should not drain. At the same time, it should not increase. That's why level also very important as far as safety of the system. So what are the variables that we are going to control? The feed flow rate, pressure, temperature, and this level are the four variables to be controlled. Now, this is the challenging task because it depends upon the safety, quality, quantity of production, quality of production, safety of operation. Based on that, we have selected these four variables. That is temperature, pressure, feed flow rate, and level has to be controlled. Is it possible? Then whether we have to go for inferential control, that we have to see. Yes, temperature can be easily measured, pressure can be easily measured, pressure transmitter, pressure sensor will sense and the pressure transmitter will transmit that value. Then feed flow rate can be measured, level can be measured. All the four controlled variables can be measured directly using simple reliable sensors, thermocouples, differential pressure sensors. By using all the four process variables can be controlled variable or process variable. Controlled variables can be easily measured. Therefore, the measured variable for the control system are T, P, temperature, pressure, feed flow rate, and the level. From the set of 2n plus 1 unspecified variables. Now, the another challenge is, what are the manipulated variables to control these four variables? What are the manipulated variable? What manipulated variable you have to use to control T? What manipulated variable you have to use to control P? Similarly for F, similarly for H. What are the manipulated variables that we have? Clearly, these are all feed flow rate. Suppose you want to control feed flow rate, means in a flow process, what we are doing is we are measuring the flow rate and controlling the flow rate. So to control feed flow rate, the feed flow rate can be used. To control temperature also, feed flow rate can be used, because if we decrease the constant temperature injected into the system, let us go to that diagram. Here, here the feed is entering here. The heat is injected by the steam. Steam is the entering, supplying heat to this system through reboiler. It is this will supply heat to this liquid, the steam. That's why the WS, the mass flow rate of steam, will supply heat to this. Heat to this, and temperature, pressure, the feed flow. Suppose you want to control level means the bottom flow rate is another product. Suppose in that example that we have seen, that let us assume that feed consists of diesel and petrol. You want to separate these two means the diesel will be the bottom product and the petrol will be in the vapor form in the top product. So if you adjust the bottom product flow rate, that is liquid flow rate, you can adjust the level. So similarly, if you want to adjust temperature, you can adjust this vapor flow rate, or if you want to adjust pressure, you can adjust this vapor flow rate. Therefore, what are the manipulated variables that we have selected are that feed flow rate, and steam mass flow rate, then bottom flow rate, that is FL, liquid flow rate, then the vapor flow rate, because the four variables has to be controlled. Vapor flow rate. So the four manipulated variables are this is F. Feed flow rate, one manipulated variable. Another variable is steam mass flow rate, liquid flow rate, vapor flow rate. These are the four manipulated variables. Now, which manipulated variable should be used for which process variable? That is another question. Why that question arises is, I will see that. Suppose feed can be used to control feed flow rate. That is obvious. To control F, we can use F. If you manipulate FF, automatically FF will be controlled. That is obvious. Suppose I want to use to control temperature, feed flow rate. Yes, very much possible, because for constant heat input, this is constant. At steady state, constant heat is injected inside. In that case, if you decrease the feed flow rate, temperature will increase. If you increase the feed flow rate, temperature will decrease. Therefore, this can be used to control, this feed flow rate can be used to control temperature also. Similarly, if you increase the feed flow rate, pressure inside will increase. If you decrease the feed flow rate, pressure will decrease inside. That is also obvious. So this feed flow rate can be used to control pressure also. Then level, if feed flow rate decreases, definitely level will decrease, because it is coming from, it is separated liquid and vapor. If feed flow rate increases, definitely level will increase. Feed flow rate decreases, level will decrease. So feed flow rate can be used to control all the four variables. So for which it should be used, that is that we have to see. Similarly, for WS, if you consider the steam mass flow rate, for example, if I increase this steam mass flow rate, what will happen? Definitely temperature will increase. Not only that, if you increase that, temperature increase that, because of that more vapor, that's why pressure also will increase. That's why WS can be used to manipulate both P and T. And is it possible to increase liquid flow rate? Yes, because if you increase this WS, it quickly separated. That's why you can take more liquid flow rate out. That's why WS can be used. Suppose WL, WS can be used to control. Sorry, what are the cross variables? Let us write that cross variables here. F, T, P, and then H, and one more, feed flow rate. So FL can be used to control all the four. How? WS can be used to control all the four. Later we'll see FL and FE. Yeah, WS. If you increase WS, temperature will increase. If you increase WS, pressure will increase. If you increase WS, more vaporization, that's why the H will decrease. That's why WS can be used to control H also. If you increase WS, more pressure will be generated. That's why downstream pressure for that feed will increase, so that feed will decrease. So WS can be used to control all the four. Similarly, FL. FL is another manipulated variable. If you use FL, the liquid flow rate, if you decrease, what will happen? Pressure will increase. So it will, if you decrease the liquid flow rate, definitely pressure and temperature will increase. That's why by using FL, we can control pressure and the temperature. If you decrease that, level definitely will increase. So level also can be controlled. And if you decrease this, what will happen? More pressure will develop. That's why vapor flow rate will increase. And as pressure increases, feed flow rate will increase, will decrease. If this decreases means pressure increases, the feed flow rate will decrease. So in the same way, FE also we can see if more vapor is taken out, if you increase the vapor flow rate, definitely there will be decrease in pressure. Temperature will increase. So pressure decreases, temperature increases, take more vapor. Mm, so more heat is taken away, temperature also will decrease this. Then if you take more vapor, the pressure here inside will decrease. That's why more feed. Then similarly, if you take more vapor, pressure decreases, more feed. That's why level will increase. So these all the four variables can be used to control all the four process variables. That's why we have to find a relation. What are the manipulated variables? Sorry, process variables T, P, then the third one is H, and FF. These are the process variables to be controlled. What are the manipulated variables available? Flow rate, FL, FV, and WS, that is also flow rate, mass flow rate of steam, and one more is feed flow rate. So four manipulated variables are there. Now, how to map this and this? How to map this and this? That we have to see. That we have to see to have a effective controller. That we are going to see. For example, alternate loop configuration. Suppose we are having only two outputs, two MIMO process, two input, two output MIMO process means, suppose to control Y1, M1 can be used. To control Y2, M2 can be manipulated. Or to control Y1, M2 can be manipulated. The same process, M2 can be manipulated. Similarly, to control Y2, M1 can be manipulated. So the two configurations. Only two input and two output. That's why only two configuration. If there are four process variables and four manipulated variables, the number of possible combinations. If you can make these type of combinations for this four MIMO process means it will be 24. It will be 24. 4 factorial. There are 24 different configurations we can have. If it is n equal to 3 means 3 variables has to be controlled, 3 process variables and 3 manipulated variables means 6 possible combinations are there. If it is n equal to 5 factorial, there are 120 different configurations are there. So out of these 24 possible combinations, we need only 4. That judicially we have to decide what are the 4 combinations that we can take. That is called alternate control configurations. From that, how to select 4 best combination. For that, what and all we have to consider? Choose the manipulation that has direct and fast effect. We have seen 4 cases. If you want control feed flow rate, I want to control feed flow rate. There are 4 manipulated variables. One is feed flow rate, Another one is temperature. Third one is pressure. Fourth one is WS. Which has direct and fast effect? Definitely feed flow rate only. Definitely feed flow rate only. So this gives a fast and direct effect. These are all indirect effect. If temperature increases, pressure inside will increases. That's why feed flow rate decreases. Pressure increases. Then also pressure inside decreases the feed flow rate. Then steam flow rate increases. It will produce more pressure, more vapor. So pressure increases. Downstream pressure, because of high downstream pressure, FF will decrease. These are all indirect effect. So FF has to be considered for FF. Choose the coupling so that there is a little dead time between every manipulation variable and the corresponding controlled output. Suppose you know that the dead time between FF and FF is nothing. So similarly, so here suppose you are using T and F means that there is a dead time. FP and FF means then little not much appreciable dead time. Here a lot of better time because steam supplied, then vaporization because of the pressure changes, then the feed flow rate has to change. These are all indirect effect. So it should not have any dead time between that we have to consider, and little dead time between the every manipulation and corresponding control variable. The third one is select coupling that has the interaction of the minimal interaction. Now we have to see what is mean by interaction. Interaction means suppose I want to control temperature because of the deviation, I want to increase the temperature. What I will do automatically, definitely, suppose temperature is controlled by WS, uh, steam mass flow rate. Because of the steam mass flow rate, if I increase steam mass flow rate, definitely temperature will increase. As temperature increases, definitely pressure also will increase. So, if already we have seen that these all four variables can be used to control all four cross variables. That's why each has some effect on the other variable. So, if you adjust one, other three also will be changed. That is called disturbance because of changes in one particular process variable. That is called interaction. If you are adjusting one, for example, I want to adjust temperature. In that case, if I adjust temperature for small changes in WS, there is a large change in pressure means I cannot control temperature by WS. Any change in WS, quickly T changes, but slightly P changes means I can use WS for T. If for small changes in WS, P is quickly changes means definitely I should use WS for P, not T. So these are all we have to judicially decide what are the four manipulated variables we have to use to control the given four process variables. These are the 24 possible combinations for given four process variables. What are the process variables? Feed flow rate, pressure, temperature, and the level. These are the four process variables. What are the four manipulated variables? FF. The first combination is FF can be used to control FF. FL for liquid flow rate for pressure. That steam mass flow rate for temperature, then vapor flow rate for H, like that. I can put the first one. Second one, the same for feed, the same liquid for pressure, and here this temperature I am changing to vapor flow rate, and this WS for H. If I change, I'll get second combination like that. Sorry. 24 possible combinations are there, out of which what are the combinations we have to consider. Among them, we have to select one. So what and all can be rejected, that we will see now. The effects of FF, FE, FL on temperature T are indirect. The effects of FF, if you increase FF, temperature will decrease, indirect effect. If you increase vapor flow rate, temperature will decrease. Pressure, temperature will change. Similarly, for FL also temperature will change. But all these three have an indirect effect on T, not direct effect. But WS is the direct fast effect. WS is the steam mass flow rate that gives immediate, it injects the energy into the flash drum. That's why WS has to be used for T. Therefore, from 24 loop configurations, only 1, 3, 7, 9, 14, 18 are look promising for efficient temperature control. If you consider temperature control only 1, 3, 7, 9, 14 and 18 are the only promising efficient temperature control. So now if you consider the effect of steam flow rate and FL on the pressure P, this WS effect of WS, FL, WS and FL on the pressure P are also indirect. If you increase WS, temperature will increase, because of that pressure will increase. If you decrease the liquid flow rate, pressure will increase because of less space, pressure will increase. Like, these are all indirect effect. But feed flow rate and vapor flow rate are better manipulated variables for controlling P, because if you decrease vapor flow rate, pressure will increase. If you decrease vapor flow rate, pressure will increase. If you increase vapor flow rate, pressure will decrease. So similarly, feed. If you increase the feed, pressure will increase. If you decrease the feed, pressure will decrease. So these two, any one of these two can be used. So from this 6, we now from 24 we selected 6. From that, if you consider that FF, feed flow rate, and FP for pressure, then another 2 is eliminated. Only remaining 4 are there. 3, 7, 9, and 14. Only 4 we are getting. So now among 3, 7, 9, 14, the loop configuration 3 seems to be best, because it uses FL to achieve the level. You know that to control level, we have to consider liquid flow rate. Liquid flow rate, that will give better control over F. In that case, 3 is best. So out of 24, if you consider 3, what are the variables that we are using? That so for FF, pressure, FV, so vapor flow rate will control pressure. The steam mass flow rate will control temperature, and liquid flow rate, the liquid flow rate will control the level. So this is the best. So now we can select F to control FF, that we can decide. Similarly, to control pressure is the process variable, the manipulated variable, vapor flow rate, top product. And to control temperature, the steam flow rate, WS, steam flow rate. To control H, it is better to manipulate FL. So these are the 4 variables that we have selected from out of 24 possible combinations. Suppose you want to um, this concept can be extended to interacting units in a plant. What you can do is the plant can be separated into small units, interacting units. Determine the degrees of freedom and the number of controlled manipulated for each block. You are separating a plant, complete plant, into so many blocks, up to this one process, up to this one process, up to this one process, like that. This is unit 1, unit 2, unit 1, unit 2, unit 3, like that. Each unit you find the degrees of freedom, and then for this you put some, select the process variable and manipulated variable and control loops. For example, if you see from first to second, it supplies some liquid from here mean. The upstream pressure is the upstream pressure of the liquid coming from here is decided by first unit. That's why it is externally specified. Externally specified. So like that, you can find the degrees of freedom for the second unit. You can decide the number of loops. Determine all feasible loop configuration for each block. What are the feasible loop configuration for each block? Recombine the blocks. After fixing, recombine all these. If any conflicts are there, remove that. This is the conflict that we will see. For example, I separated unit 1 and unit 2. Unit 1, I want to control the liquid flow rate by using that liquid flow rate. For unit 2 also, the controller is this is one configuration. This is in unit 2, this is one configuration. Some other liquid is manipulated to control unit 2. Suppose we selected such a way that the outflow rate of this first unit is controlled to control second unit, means the first unit also control the same flow rate, second unit also control the manipulate the same manipulate the same flow rate. First unit also manipulate the same manipulated variable, but in series. Suppose this unit want to decrease this flow rate, and this unit want to increase the flow rate. Depends upon its disturbances. Depends upon its disturbances. It wants to decrease. It wants to increase, means a contradiction. That's why we have to remove all these conflicting control loops, and we have to consider like this. Then for this, here we are using this liquid flow rate control. Here some other process also gives some liquid to this, that has to be controlled to control this second unit. So, he asked, is there any algorithm to choose the MIMO class variable, or are you asking manipulated variable? Is there any specific algorithm choosing variables? Generally, he said variables. There is no algorithm. We know what are the variables. We know what are the variables for a particular process. All possible variables we have to list out first. What are the possible variables in this process? We have to list out. First, for example, that feed flow rate, temperature, temperature of the feed, like that. In a chemical process, what are the variables that you have to list? There is no algorithm for that. There is no algorithm for that. If we list out those variables, then only we can find a relation among the variables. We can find a relation among the variables. That is called the mathematical model of the process. So what is mathematical model? Relating the variables of those of the process, variables of the process, called a mathematical model. And this mathematical model either may be from experimental result or maybe from the first principle, fundamental first principle. So there is no algorithm. That what are the variables available for that process is natural. So from that we have to consider, but we should list out all possible variables and all possible equations. Then only we can correctly find the degrees of freedom. I think you agree with me. What is mean by n in degrees of freedom? N. Yes. We'll go to degrees of freedom. N in degrees of freedom. What is mean by n in degrees of freedom? N means number of equations here. So here number of variables, for example, the composition, n possible compositions are there. That's why here we are getting this n. N number of equations. For example, depends upon the composition in this. We are having how many equations? N minus 1 equations. Because of that composition, we get n equations for xi and n equations for yi. So n is number of equations here. Number of equations. So generalized. So it may be 10, 5, 4. So this is generalized model. That's why n is not specified. It is number of equations. Number of number of variables, sorry, number of variables x suffix I. That's why this is in the component balance it will come. If you want to know about exactly n, you should ask. You have to take a particular process or particular chemical, and you should ask the chemical engineer what is the value of n. You have to ask. But in this case, we are considering it consists of n compounds. That's why it varies from 1 to n. Thank you.